Welcome to our deep dive into solubility, a fundamental concept in Class 12 chemistry. Solubility plays a crucial role in understanding how substances interact in solutions, whether in the lab or in everyday life. Today we'll explore what solubility means, the types of solutions you'll encounter, and the various factors that influence how much of a substance can dissolve. By the end of this video you'll have a clear grasp of why some substances mix easily while others don't, and how temperature and pressure come into play. Let's start by defining solubility and seeing how it's measured. Solubility is defined as the maximum amount of solute that can dissolve in 100 grams of solvent at a specific temperature to form a saturated solution. This definition helps us quantify how much of a substance can be mixed into a liquid before no more will dissolve. For example, if we say the solubility of sodium chloride or table salt in water at 25 degrees C is 36 grams, it means that exactly 36 grams of salt can dissolve in 100 grams of water at that temperature. Any more and the excess will remain undissolved. Let's look at a practical example to make this clearer. The solubility of sodium chloride or NaCl in water at 25 degrees C is 36 grams. This means if you add 36 grams of salt to 100 grams of water at this temperature, all of it will dissolve, forming a saturated solution. If you try to add more salt, it won't dissolve and will settle at the bottom. This simple example helps us visualize how solubility works in real life and why measuring it is so important in chemistry. Solutions can be classified based on how much solute they contain relative to their solubility limit. Understanding these types helps us predict how a solution will behave if we add more solute or change the conditions. The three main types are unsaturated, saturated, and supersaturated solutions. Each type has unique properties and plays a different role in chemical processes. Let's break down what each term means and how you can identify them in practice. Unsaturated solution is one where more solute can still be dissolved. In other words, the solution hasn't reached its maximum capacity for dissolving a particular substance. For example, if you add a spoonful of sugar to a glass of water and it all dissolves, the solution is unsaturated. You can keep adding sugar until it no longer dissolves. Unsaturated solutions are common in everyday life and are the starting point for many chemical reactions. Saturated solution contains the maximum amount of solute that can dissolve at a given temperature. If you try to add more solute, it simply won't dissolve and will remain as a solid at the bottom. This is the point where the solution is in equilibrium with the undissolved solute. Saturated solutions are important in chemistry because they help us determine the solubility of different substances under various conditions. Supersaturated solutions are a bit unusual. They contain more solute than should be possible at a given temperature, making them unstable. This can happen if you dissolve extra solute at a higher temperature and then cool the solution down. The excess solute stays dissolved temporarily, but any disturbance can cause it to crystallize out suddenly. Supersaturated solutions are fascinating and are used in making crystals and in some industrial processes. Now that we know what solubility is and the types of solutions, let's explore the factors that affect how much solute can dissolve. These factors include the nature of the solute and solvent, temperature, and pressure. Each of these plays a unique role depending on whether you're dissolving a solid or a gas. Understanding these factors helps chemists control reactions and design better products. Dissolving solids in liquids, the nature of both the solute and the solvent is crucial. The rule of thumb is like dissolves like. This means polar solute dissolve best in polar solvents and nonpolar solute dissolve in nonpolar solvents. For example, table salt NaCl, which is polar, dissolves easily in water, another polar substance. However, it won't dissolve in benzene, which is nonpolar. This principle helps explain why some substances mix while others don't. Let's take a closer look at the example of NaCl in different solvents. Sodium chloride dissolves easily in water because both are polar. But if you try to dissolve NaCl in benzene, which is nonpolar, it won't work. This demonstrates the importance of matching the polarity of solute and solvent when trying to dissolve a substance. It's a key concept in chemistry and helps us predict solubility outcomes. Temperature is another major factor affecting the solubility of solids and liquids. For most solids, solubility increases as the temperature rises. This means you can dissolve more sugar in hot tea than in cold tea. The particles move faster at higher temperatures, making it easier for the solute to break apart and mix with the solvent. This is why heating is often used to speed up the dissolving process in labs and kitchens alike. Simple way to see temperature's effect is by adding sugar to tea. In hot tea, sugar dissolves quickly and in larger amounts. In cold tea, it dissolves slowly and less sugar can be added before reaching saturation. This everyday example shows how temperature can make a big difference in how much solute a liquid can hold. It's a principle that applies to many substances, not just sugar and tea. When it comes to dissolving solids and liquids, pressure doesn't have a significant effect. Unlike gases, where pressure can greatly influence solubility, solids remain mostly unaffected. This means that increasing or decreasing the pressure won't noticeably change how much of a solid can dissolve in a liquid. This is an important distinction to remember when comparing the solubility of solids and gases. Solubility of gases and liquids depends heavily on the nature of both the gas and the solvent. Polar gases dissolve better in polar solvents, while nonpolar gases prefer nonpolar solvents. For example, ammonia NH3, a polar gas, dissolves much more readily in water than oxygen O2, which is nonpolar. This difference is crucial in many natural and industrial processes, such as water treatment and respiration. Illustrate, let's compare ammonia and oxygen in water. Ammonia, being polar, dissolves easily in water, which is also polar. Oxygen, on the other hand, is nonpolar and doesn't dissolve as well. This explains why certain gases are more soluble in water than others, and why the composition of dissolved gases in natural water sources varies so much. Temperature affects the solubility of gases in liquids in the opposite way compared to solids. As temperature increases, the solubility of gases decreases. This means that hot water holds less dissolved gas than cold water. This is why you might notice fewer bubbles in a glass of warm soda compared to a cold one. The higher energy at elevated temperatures allows gas molecules to escape more easily from the liquid. A real-world example of this principle is seen in aquatic life. In hot water, there's less dissolved oxygen, making it harder for fish to breathe. That's why fish often struggle or even die in overheated ponds or lakes. This example highlights the importance of temperature in maintaining healthy environments for aquatic organisms. Pressure plays a significant role in the solubility of gases in liquids. As pressure increases, more gas can dissolve in the liquid. This is explained by Henry's law, which states that the amount of gas dissolved is directly proportional to the pressure above the liquid. This principle is used in carbonated beverages, where high pressure keeps more carbon dioxide dissolved in the drink until you open the bottle. Henry's law is a key concept in understanding gas solubility. It states that the solubility of a gas in a liquid is directly proportional to the pressure of that gas above the liquid. This means that if you double the pressure, you double the amount of gas that can dissolve. This law is crucial in industries like beverage production and scuba diving, where controlling gas solubility is essential. Sum up, the solubility of solids and liquids depends mainly on the nature of the substances and temperature, while pressure has little effect. For gases, all three factors, nature, temperature, and pressure, play important roles. Knowing how these factors interact helps chemists design better experiments and products, from medicines to soft drinks. Let's now look at some practical applications of these principles. Solubility isn't just a classroom concept, it's something we encounter every day. From dissolving sugar in coffee to making instant soup, understanding solubility helps us make sense of many common activities. It also plays a role in environmental science, medicine, and industry. Let's explore some real-life examples where solubility is at work. In cooking, solubility is key to making delicious food and drinks. When you dissolve salt in soup or sugar in tea, you're using the principles of solubility. The temperature of the liquid and the nature of the ingredients determine how much can dissolve. Chefs often use heat to speed up dissolving, ensuring flavors are evenly distributed throughout the dish. In medicine, solubility determines how drugs are absorbed in the body. Many medicines are designed to dissolve quickly in the stomach or bloodstream, ensuring they work effectively. Chemists must carefully consider solubility when developing new drugs, as it affects how fast and how well the medicine can be used by the body. Solubility also has a big impact on the environment. Pollutants that dissolve easily in water can spread quickly through rivers and lakes, affecting plants and animals. Understanding solubility helps scientists predict how contaminants move and how to clean them up. It's a vital concept in environmental science and public health. Industries rely on solubility for processes like cleaning, manufacturing, and waste treatment. For example, in the beverage industry, controlling the solubility of gases is essential for making carbonated drinks. In cleaning, knowing which solvents dissolve which stains helps create effective products. Solubility knowledge is crucial for efficiency and safety in many fields. Solubility curves are graphs that show how the solubility of a substance changes with temperature. These curves help chemists predict how much solute can dissolve at different temperatures. By reading a solubility curve, you can determine whether a solution will be unsaturated, saturated, or supersaturated at a given temperature. This is a valuable tool in both research and industry. Read a solubility curve, find the temperature on the x-axis and the amount of solute on the y-axis. The curve shows the maximum amount that can dissolve at each temperature. If your solution is below the curve, it's unsaturated. On the curve, it's saturated. Above the curve, it's supersaturated. This simple tool helps chemists make quick decisions in the lab. Supersaturated solutions are unstable, and any disturbance can cause the excess solute to crystallize out. This process is called crystallization. It's used in making rock candy and purifying chemicals. By carefully controlling temperature and concentration, chemists can grow large, pure crystals for use in industry and research. When two solutions are mixed and an insoluble product forms, it's called a precipitation reaction. The insoluble product or precipitate forms because the solubility limit is exceeded. These reactions are important in water treatment, chemical analysis, and even in forming geological features like stalactites and stalagmites. Solubility product, or KSB, is a constant that describes the equilibrium between a solid and its dissolved ions in a saturated solution. It's used to predict whether a precipitate will form when two solutions are mixed. KSB values are unique for each substance and are essential in analytical chemistry. The common ion effect occurs when a solution already contains an ion that is part of the solute being added. This reduces the solubility of the solute as the solution becomes saturated more quickly. The common ion effect is important in controlling reactions and in processes like water softening. Temperature can also affect precipitation reactions. In some cases, increasing the temperature increases solubility, preventing precipitation. In other cases, cooling a solution can cause a solid to form. This principle is used in purifying substances and in the formation of minerals in nature. The pH of a solution can influence the solubility of certain substances, especially those that can react with acids or bases. For example, some salts dissolve better in acidic or basic conditions. This is important in environmental chemistry and in designing chemical processes. Some substances form complex ions in solution which can increase their solubility. For example, silver chloride is only slightly soluble in water, but adding ammonia forms a complex ion that dissolves much more easily. This principle is used in analytical chemistry to separate and identify ions. The ionic strength of a solution or the concentration of ions present can also affect solubility. High ionic strength can either increase or decrease solubility depending on the substances involved. This is important in biological systems and industrial processes where many ions are present. Hydration refers to the interaction between water molecules and ions or molecules of the solute. Good hydration increases solubility as water molecules surround and separate the solute particles. This is why many ionic compounds dissolve well in water, making it a universal solvent. The size of the solute molecules can also influence solubility. Smaller molecules tend to dissolve more easily than larger ones as they can fit between the solvent molecules more readily. This factor is considered when designing new chemicals and materials. Polarity is a major factor in solubility. Polar solutes dissolve best in polar solvents while nonpolar solutes prefer nonpolar solvents. This is why oil doesn't mix with water but sugar does. Understanding polarity helps chemists predict and control solubility in various situations. While most solids become more soluble as temperature increases, there are exceptions. Some salts like calcium sulfate actually become less soluble at higher temperatures. It's important to check solubility data for each substance as general rules don't always apply. Although pressure usually doesn't affect solids and liquids, there are rare cases where very high pressures can change solubility. These situations are mostly found in geological processes deep within the Earth, where extreme conditions can alter chemical behavior. Miscibility is a related concept that describes whether two liquids can mix in any proportion. For example, water and ethanol are completely miscible while oil and water are not. Understanding miscibility helps chemists design mixtures and solutions for various applications. Solubility plays a vital role in natural processes. It affects how minerals dissolve in water, how nutrients move through soil, and how gases are exchanged in the atmosphere. Understanding solubility helps scientists study everything from the water cycle to the health of ecosystems. In the water cycle, solubility determines how salts and minerals are carried from the land to the sea. Rainwater dissolves minerals from rocks and soil, transporting them to rivers and oceans. This process shapes landscapes and supports aquatic life. Solubility affects human health in many ways. It determines how nutrients and medicines are absorbed, how toxins spread in water, and how our bodies maintain balance. Understanding solubility helps doctors, pharmacists, and scientists protect and improve our well-being. Solubility is a foundational concept in chemistry, with wide-reaching effects in science, industry, and daily life. From understanding how much salt can dissolve in water to designing new medicines and protecting the environment, solubility is everywhere. By mastering the principles of solubility, you gain powerful tools for exploring and shaping the world around you. Keep these ideas in mind as you continue your studies and experiment.